It's all yours.
Thank you. Yeah, I am brain frozen, so let's see. Okay, so again, thank you once more for being here. Is there a, do you want me to do something with the mic or? Okay. Is this better? Okay, I continue on. Post-processing takes care of the optimal POVMs are chosen. Okay, so I think the plans are a bit modified, so I might not get around to everything that I want to get around to. I have 55 minutes, but I'm here tomorrow. We can chat. All I want to do is work out just a couple of simple things. The things that I have not seen very easily when I basically was first trying to find the literature. And in fact, even now when I was preparing for this, these results are written somewhere, and then it's not, it's not straightforward where to see these results. So in fact, I'll present maybe one of them, which I think was interesting for me to work out. So again, the plan is as follows. I'll just recap a little bit of what we did yesterday, and then continue from there. So I'm still giving these basic lectures on right? But the point here is basically that a lot of these techniques and ideas are quite applicable. You can carry them. You can, of course, serves the purpose at hand, but also it's more general than. Okay, so what I had basically discussed thus far is this quantity and being defined basically as some trace over some measurement operator times some quantum state. And this quantum state basically you can choose it that way. That would be that would get you to a lot of the initial work in this, and you could choose this, for instance, to be a pure state, and that will get you even further. So and in that case, you could choose this to be something like that. Okay, so I just want to say just a couple of remarks about what we are doing here. So in all of the diagrams that you saw through the week, so on and so forth, there was always basically some sort of initial state, and it's typically a fixed state. So, and it's typically a fixed state because if I don't fix the state, so do all of you know this? Do you know what the logic of this argument is? So the logic of this argument is the following, which is in quantum computing, but also in all kinds of other places, you can hide resources. If I don't make you technically account for them, you can hide resources, right? And one of the ways in which you can hide resources, you can say, hey, I have a highly entangled state here, and then I can do magic with it, right? So you heard in several of the talks, Carl's talk, Saikat's talk, Anil's talk, Saikat's second talk, all of kind of quantum computing, but in this context, metrology is all about careful resource accounting, because you can do in principle whatever you want, which is you can measure any quantity, to arbitrary accuracy that physical law allows you to, but you just have to, spend you'll waste a lot of resources getting there unless you kind of know the physical theory very well and the estimation theory very well, and you can optimize over, right, the various parameters. So the task at hand is that I give you one such quantity, and you can apply anything you want, any unitary that you want that prepares it. An example of this is the circuit that you've been seeing all week, where you have a Hadamard and then a control knot, right? And this is set up in such a way so that I can explicitly point at some part of the interferometer as to the part of the interferometer that's generated the entanglement for me, right? And if I didn't do it, if you were not made to do it, then it's happened. I can point at the papers to you offline, where somebody would initially write, like in the late 90s, early 2000s, here is some magical state that does, here is a magical metrology scheme that does something very nice. And you would stare at it and go, oh, that's very nice. What is the relationship of this to all of these other things that I've learned? And it turns out that the magic was hidden in the fact that this circuit was not properly explained. So they assumed some quantum state, which is very complicated, right? And then off they went and then produced some very nice results. So as a kind of thumb rule, computer scientists do this all the time. As a kind of thumb rule, you're not allowed to kind of process your initial state. You're supposed to set it to some fixed state, and the ground state's a good enough state to fix it at, right? That's the reason why this is always in all of the circuit diagrams a fixed state. And then what is said to you, what is said to me, is you can do whatever you want. You have to account for the resources, but you can do whatever you want. And a lot of the literature in metrology is basically, what is the cost of generating this entanglement, right? How many circuits do I need? What is the, how complex are they to make? Blah, 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 so on and so forth. And after this is done, you typically have some stage where you have these N modes coming out. Now, perhaps they're entangled if I've chosen this method to do. And now you can also choose how you want to acquire the phase. So you can acquire it like this, right? Which is just sigma Z1 plus sigma Z2 plus sigma Z3, so on and so forth. Typically the way that you would consider it naturally to be the way that phase is acquired, but you don't have to do it this way. In fact, Anil's entire talk was, what if you left this universe and started doing slightly more interesting things, right? Started using nonlinear Hamiltonian, so on and so forth. And there are some remarks here, which I just want to point at. So there is a very famous paper by, I think it's Zweis. I'm sorry, I should have written the name down. Zweis, whose name I should know to spell, but I do not. I believe, and Koch, it's a PRL. And so if you search, you'll find it, where they basically use query complexity. It's in the Sidhu and Koch review cites this paper. So they basically point out something very interesting, which is they say, if you think of a black box, which has the phase sitting inside it, so it's a beam splitter, and now I've given you a box, and the box has a input port and an output port, right? And now I ask you to find some property, the transmission coefficient of this box. Every time you use it, every time you send light into it, you have to pay me, right? So then the cost is the number of users, right? Is proportional to the number of users. So this is related to this idea of query complexity, right? And so what they point out is that the query complexity is the important thing to discuss here. So in this context, just to add to one comment to the nice talk that Anil gave today morning, is to basically say, if I take this, I can generalize. I can say the Hamiltonian that he wrote, for instance, is Jz squared, right? And the Jz squared Hamiltonian is sum over sigma Zi, sigma Zj, I and j going from 1 to n, right? How many terms are in this? It's the number of pairs I and j, right? Right? Yeah, it's n into n minus 1, right? So n into n minus 1 over 2. And so this, basically what this does is it essentially tells you order n square is the number of times you're asking the question, what's the phase, right? So if my Hamiltonian is that, you can interpret this in the query complexity language as asking the question, what is the phase? Order n square times. And that's the reason that you have the super Heisenberg scaling that we talked about today morning, right? So this optimization is about entanglement, right? Perhaps it's about entanglement, perhaps it's about Fisher, perhaps it's about something else, but let me just say entanglement is a kind of placeholder for the variety of quantum correlations that we're interested in generating in quantum technologies in general, and specifically for the case of metrology. This is about basically, I'll call it queries, right, as a kind of placeholder to say it's about the varieties of different Hamiltonians that are available in natural systems, the varieties of phase acquisitions that you could, that you could perform, and the varieties of Hamiltonians that you could choose, right? So even in one physical system, driving it weakly versus driving it strongly produces slightly different answers. And then once the phase is embedded on the quantum system, I want you to be with me in this point, that this is as well as you could have possibly done, right? For a given choice of the initial state, which is the fixed state plus entanglement, right? And for a given choice of Hamiltonian that once I fix those two, I can't do any better. All the phases already in my quantum state, right? What is now what all could I do? I could read something very bad, right? So my readout could be extremely bad. So here, for instance, I could essentially just not read the correct thing. So for instance, I could read, let's say, put it a beam splitter, if I think of this as a kind of photonic, polarization degrees of freedom. And I could basically read something which is not particularly interesting. Like I was giving an example, if the total number of photons is conserved in a Hamiltonian interaction, you could, counting the total number of photons doesn't tell you anything, right? So you could make bad measurements. This is all I'm trying to say. So all that happens after this box leaves is you may get the best measurement or you may not, right? So this, the way that we encode is by drawing a unitary. This unitary essentially prepares the measurement basis. So what I'm doing is, again, because I can hide a lot of post-processing in the measurement, it's good to have kind of standard basis measurements, something like just up and down spin polarization, right? Or number counting, whatever. And then basically embed all of the difficulty of your measurement basis into this box V. So the thing that I've just outlined, put a box around in white chalk, is basically the choice of measurement setting, right? So in all of the talks that you've heard this week, when you hear, here is the optimal measurement, or here is the POVM that you should be implementing, or here are the projectors that you should be, that's the game you have to play over there, right? If it's some measurement over all of the quantum state, then you have to perform the rotation B, and then, right? And perhaps you will be asked to account for the amount of resources you used up there. Okay. So in this context, basically, if I stop here, I can ask the question, how best can I do? How best can I do given a choice of rho naught and given a Hamiltonian G, right? This question is answered by the quantum Cramer-Rao bound, right? And so the mathematical derivation that I did last time, which I just write for this thing is the quantum Cramer-Rao bound. And this is the fundamental quantity we are interested in. right? The mean square error of the estimator. And it's upper bounded by, usually the thing that is presented is the denominator, which is the quantum Fisher information, right? So this quantity, which is the quantum Fisher information, right? Which has many, so Saikat called it J of phi, right? I called it, I think, FQ. Sometimes rho naught and G are put in here so that if we are comparing different schemes, so if you read papers and you're saying, I have a scheme which has entangled states, or I have a scheme which has linear Hamiltonians, something that has nonlinear Hamiltonians, how do I compare these? Then people will write everything in here into the FQ, load it up so that you can read it. You know, from the information community, it's also called I sometimes, maybe IQ or IC, so on and so forth. So all of these labels mean the same thing, and now you know. I want to make several points here, which I could not last time. The first of these I have already made, which is that this is the quantum Fisher information. The second of these I want to make is that if del theta of b theta is greater than 0, then all you're going to do by having a biased estimator is hurt yourself, right? Because the numerator is bigger than it needs to be. You want to make the numerator as small as possible, make the denominator as big as possible. The numerator is now bigger than 1. Now, so the only way in which it helps, so this is very bad. And that's the reason why we discuss unbiased estimators, because it makes our life simpler. But if you look at the full literature, of course, so if del phi is b phi, definitely this machinery is indicating that you're winning, but you have to think a little bit about all the different aspects. Is it implementable, so on and so forth, right? Okay. And the very last point I want to make is this point I want you to carry away as we're discussing all of this stuff. So typically, if I have a quantum system which has basically, this is all scaling with n is the thing that you've been discussing, right? I'll get back to the scaling with n. But just in visually, I want to draw a line where this is the classical bound of classical Cramer-Rao bound, right? And typically what you have is, you have somewhere over here, the quantum Cramer-Rao bound, right? Not the Cramer-Rao bound, but classical Fisher information. And the quantum Fisher information is larger than the classical Fisher information, right? And typically it's somewhere, you know, I'm not drawing any scale on this, so it doesn't make sense. This is a cartoon. What I want to say is, I want to call this the theoretical, right? And I want to make just one more point or two more points, which is there may be a gap between this and the experimentally accessible quantum Fisher information and the theoretical quantum Fisher information. This gap is 0 for single parameter estimation. But for multiple parameter, you can have this non-commutativity, blah, blah, right? And most importantly, for those of you who are experimentally inclined, there may be something sitting over here, which is so experimentally convenient, right? So given the resources in your lab, given the standard resources in the community, what's known, what's achievable, what's good, so on and so forth, a very case-to-case affair. there could be an even further gap, right? And so when you're looking at the literature or when you're thinking about these things, when I'm thinking about it, I always pay attention to the fact that I'm calculating what's the best it could be, right? But there is all this other stuff here, right? And both these experimental things are very model dependent, you have to tell me exactly what you're doing. Okay. So with that, I'm done with what I wanted to say last time. I will begin this time with a series of formula. So I'll write these formulas down, and then I'll actually show you how to derive them in a little bit. Okay. Let me do it the other way around, actually. This makes more sense. Just give me 1 second. Okay. So what did we just discuss? We discussed the quantum fish information, right? Let me call it something. Is equal to basically the trace of L phi squared acting on rho phi, where L phi rho phi plus rho phi L phi by 2 is delta rho phi by delta phi. So what am I supposed to do with this equation? What's the step forward? I mentioned it last time. Does anyone remember? Okay, so again, a point of personal taste, but when I was looking at this, when I was trying to first learn this literature, this was the scariest piece for me. This was where it points to basically something called a matrix Lyapunov equation. That points to some books. It goes off into the ocean, basically. And so I always took it as a piece of faith, right? And so I show you the derivation, which is, I think this is correct. I'm happy for you to tell me if I've missed something. Okay. So how do you do this? So let's write L phi as basically some sum over ij, aij, right, times some basis. What's a good basis to choose? You don't know the readout basis. I mean, the whole problem, right? So we haven't finished optimizing, so you don't know what the fish information is. So you don't yet know what the SL, right? Okay. So what I will do is I'll just point at the only matrix that's given to us, which is rho of phi, right? So let me write rho of phi as sum over lambda phi, lambda phi, lambda phi, very classic overloading. Sorry, let me remove the phi and just write it as lambda k, lambda k, lambda k. The phi is implied. Right? Remember that fish information depends on the parameter, right, in general. And so the density matrix at that value of parameter is like some unitarily rotated initial state. So in general, its eigenvectors depend on, right? And if it's an open quantum system evolution, its probabilities could also depend on phi, right? And that's the reason why I've written this in the most general possible fashion. And so I'll use this basis to write this, right? Because rho is a Hermitian operator. This is okay. Yeah, I'm allowed to do this. And then what I'll do is I'll just take derivatives. What is this? This is sum over del lambda k times lambda k, lambda k. I'm just using this shorthand notation, plus sum over k, lambda k, del lambda k, lambda k plus lambda k del lambda k. I've done nothing yet. Yeah. Then what I'll do is I'll equate this to and I've dropped, L is L of phi, but I've dropped that phi as well. I'm just being maximally lazy. Yeah. So I'll equate these two, right? Because that's what the equation says, right? But what is L? I've just written it in this Aij basis. So this is sum over ijk times Aij lambda I lambda j, right? And then I have to write rho phi, but that's lambda k lambda k lambda k. And then I have the other object, which is Aij lambda k lambda k lambda k times Aij lambda I lambda j. Yeah, and then let me just put a half up front. Good. So this equation is equal to this equation. We're almost at the answer, right? You can see it. So all you have to do is you just take on both sides, basically, a lambda I equation. Let me just check exactly what I've done. Yeah. L rho plus rho L by 2 lambda j. Simply ask what is this quantity? Yeah. So when you do that, what you get is you have to do it essentially in two pieces. One for the diagonal term I equals j, and one for the off diagonal. So let me just write the answer, and you can work out that that's the answer. The answer is half okay. Yes. Okay. So half lambda k times basically lambda I d lambda k lambda k lambda j plus lambda I lambda k d lambda k lambda j, and this yeah, okay, this is the way I wanted to write it. Okay, so this is for off diagonal, and this is equal to half of Aij lambda j plus Aij lambda I. So this, there is no half here because this is just the derivative of the expectation value of the derivative. Okay, so let me just explain in one word what I did. Everything here, this d lambda lambda d lambda lambda is basically this term. So this term, remember, actually is d lambda k is a change of lambda k. It's the parametric derivative of the eigenstate lambda k with respect to the unknown parameter, right? And this d lambda k does not have to be lambda k. It does not have to be lambda k prime. It's in principle some superposition over many states, right? So that's the reason why d lambda k you cannot touch. You cannot take orthogonality assumptions with it. On the other hand, the this probability derivative delta lambda k is delta lambda k by delta theta on lambda k. That's diagonal. So I just dropped it from here because I'm just doing off diagonals. Yeah. So this is just the derivative of the parameterized density matrix with respect to the parameter phi. And on the right hand side is what it should be in terms of the elements of the L matrix multiplied by things that I have no control over, right? Which is the eigenvalues lambda. Everything is parameterized, right? Okay, good. Is this clear to everyone? And the diagonal term, what is the diagonal term? This is equal to del lambda k plus lambda k times lambda k del lambda k plus del lambda k lambda k. Okay. So right, doesn't matter what the parameter is. Which means if you take a derivative, the right hand side is 0. And what this means is that I can drop this term. Right? Normalized vector, so it doesn't. Okay. And so now I just need to collect all of this information into one piece of calculation. And so let me present that to you. AKK is equal to del lambda k by lambda k, because remember that, oh, sorry, I didn't write what this is. This is AKK lambda k for diagonals. Right? Here what I've done is I've just taken this object and I've just taken the expectation value with lambda k. So I becomes k, j becomes k. That's all, right? You just need to consistently do it throughout. Okay. So this is AKK. And then Aij is 2 divided by lambda I plus lambda j times lambda j lambda I d lambda j plus lambda I times d lambda I lambda j. This object, there are 2 things I want to say. Thing number 1 is this, if lambda I and lambda j were not here, this object would be 0 because of the arguments I present. But this object is not 0 because there's this lambda I, lambda j floating around, and I not equal to j, right? And the second thing is basically there is something you have to stay away from. Lambda I plus lambda j is equal to 0 terms, right? These are the terms that, you know. And so if you look in the textbooks of quantum Fisher information derivations, classical Fisher information derivations, this statement, quantum Fisher information derivation, this statement will be there. It'll just say, for cases where this is not true, the following formula is there. And if you can say, hey, I'm very curious what is happening here. Now this is the only thing I want to work on. So on and so forth. I just want to point at a very interesting paper, which is Dominic's paper. So this is PRA 95 05 2320 2017. There's some nice discussions of what happens when the rank of the density matrix changes suddenly and some lambdas start doing crazy things. Yeah. Yes, the problem is basically that they are positive semi-definite, but still semi-definite. The exact point I was trying to make, sorry. Right, so that 0 is a troublesome guy. And in fact, the whole point I just want to make, there is a general point here, which is that you have probability distributions whose curvature you're asking, right? If the probability distribution is like P1, P2, P3, and then you change the parameter and P3 goes to 0 suddenly, it's a singular event, right? And those require special attention. We already saw a cousin of that because the classical relative entropy, the Kullback-Leibler divergence, also has this 1 over Qi, which would blow up, right? It shows up all over the place, that there is this issue when the rank of the matrix changes, right? And so this is just something to keep track of. Okay, good. So this, I believe, is the entire formula. So the answer to the question, what is L? L is the matrix Aij, lambda I, lambda j, with the A matrix defined above. Right? And did I use any assumptions about what the density matrix was? Nothing, right? There's just this assumption that's built in. So you can apply this to open quantum systems. Those of you who are doing master equation calculations, so on and so forth, right? I have some parametrized Hamiltonian, phi times g, and then I have some Lindblad terms. Then in general, basically, if you can write down what the quantum state is, then you can apply this. You can apply the distance between, the Bureau's distance formula as well, so on and so forth. Okay. I just want to do 5 more minutes of this maths and then I'm done, which is, how do I know that I have the right formula? Right, I don't, but let me try it for one example and show you why I'm convinced that this is okay. So let's compute IQ, right, which is the same as FQ, for rho theta, rho phi, which is lambda phi, lambda phi. So lambda phi, what does this mean? Pure state, right? So rho phi is a pure state, and furthermore, I just assume that it's some unitary evolution, right? So let me compute this. Automatically, step number 1, del phi lambda k is equal to 0, because the eigenspectrum lambda k is what? It's 1 and all zeros, right? The probability of mixtures is basically, let me just take a binary that suffices to make the calculation. So this is the quantum state lambda phi. It appears with probability 1, and there is some state which I can interpret as lambda phi orthogonal that appears with probability 0, right? Only true for unitary evolution, right? And that's the case that I'm working on just now. Yeah. Okay. So in this case, what is the quantum Fisher information IQ? It's the trace of L square rho phi. But again, I know what rho phi is. It's lambda phi, lambda phi. I just put it in and evaluate it. And what is this? In general, what this is sum over the trace of A I j, A j k, lambda I, lambda k, right? So this is 2 copies of L, right? And the inner product is jj, sitting right there, summed over j. Lambda k, lambda k, lambda k. This is how I would in general evaluate it. If lambda k was on a probability distribution, was a kind of not an extremal probability distribution, summed over I, j, and k. Yeah. But there's nothing to, I mean, there's only one thing to sum over, which is this j. Because when you do this thing, the k goes here and makes it delta ik, right? And so the whole thing simply becomes sum over j going from 1 to 2, lambda 1 j, sorry, a1 j, a j1 times lambda 1. Sorry? Yeah, this is rho phi, spectral decomposition. Yeah. Okay. Do you see this? So in general, right? But then what this is there is only one lambda there, so there is no k, and there is just this guy, right? Which means there is no k here. I can remove the k. I can remove the k and put 1 there. When I move this over here, there is no I. I can put 1. I can just remove this. I can put 1 here, and I just need to sum over this. That's all I'm saying. That's that formula. But lambda 1 is 1. There's even less to do, right? What is this? This is a11 square plus a12 mod square. A11 was what? I forgot to mention this, so I'll go back here and say this to you. This should remind you right? Should remind you of classical Fisher. And indeed, that's what this is. If you keep the eigenvectors constant and only the probability distribution is changing, that's just a classical problem. And you can work out that example. And if you calculate everything here for that example, you should recover the classical Fisher information. Okay? So the classical part is what contributes to A11. Of course, it's 0, right? Because I'm doing pure unitary evolution here. Technically, it's 0 because del lambda k is 0, because lambda is just 1, right? So now I have to basically figure out what the rest of it is. And to do that, what I have to do is I have to compute what this A12 is. This A12 is 2 times d lambda times lambda perpendicular. How do you find a lambda perpendicular? I give you some vector, Gram-Schmidt, right? So if you take A, then if I want to construct a vector B, what do? I take A and then subtract from it the projector of A onto it and then normalize it, right? Okay, so if you do this here, I'll just pick a judicious choice of A and B. The choice of A that I pick is lambda, and the choice of B that I pick is right? So actually, I just need to write this down. This is right, and I have to normalize this state. I want you to notice that this is G minus the expectation value of G, right? So this object is G minus the expectation value of G times lambda. So when I divide by the normalization, it's actually the square root of the variance of G. Yeah. And so that's that quantity. So when I compute this quantity, what is this? This is lambda G, because that's d lambda. Sorry, I will choose lambda A as d lambda, not so lambda G is d lambda, right? And then what I did was d lambda is G times lambda, right? But there's an I outside, which I need to pay attention to. There's a 2 outside. And because this is appearing with a bra and not a ket, there's a minus, right? Won't matter, but let me write it. Right, G, and then I just need to plug in this quantity. And this quantity is basically right. And you can convince yourself that this is 2 times I times the square root of the variance of G, which means that the quantum Fisher information for pure states, which is basically mod which is mod A12 squared, is 4 times the variance of G. Right? This formula, I basically, if I do nothing else, oh Christ, I have 7 minutes more. Okay. If I do nothing else, I hope that this is useful to your education, because we've started from kind of a completely general definition of Fisher information, classical, right? Actually, from estimation theory, worked our way through classical Fisher information into quantum, produced the symmetric logarithmic derivative argument, actually worked out the formula for symmetric logarithmic derivative for any general quantum evolution, applied it and showed that it's 4 times the variance, right, for pure states. So this 4 times variance is something that you keep seeing all the time, right? Okay. So I have many more things to say. So I'll try and finish, but maybe I go 5 minutes longer or so. My host is not happy. I write a bunch of, I'll try and finish. So let me write a bunch of other formula which are also very useful and important, which I think you should work out. So this is one of the famous formulas, the most general formula. You can see this. This is the classical part. In general, what you get is okay. And okay, so there are several more things that I could say that I won't say. Let me just end by making a bunch of different remarks. Remark number 1. So I just want to make a quick side comment about Okay, before I make this comment. So suppose I want to apply this, like, so where do I go from here, right? So here is an example that I wanted to discuss a little bit more, but I just hint it at you, and then, I don't know, I put it somewhere, or we can talk about it offline. The reference is Peters, Chuang, and Chu. This is 2001. There are several more references, but this is the classic. Where let me not explain how this is done, but imagine that I have a stream of atoms that are coming in, right? And what I do is I arrange some light to fall on it, right? And you know that it carries momentum. You can use it to kick atoms. So let me say that I kick some atoms. In the absence of gravity, what will happen is that these atoms go this way, and I split the atoms into two. And so I apply a beam splitter transformation. I send some of the atoms this way and some of the atoms this way, right? And then what I do is I again apply one such beam splitter transformation somewhere, and then they return back here. Then what I have is basically I've arranged for a Mach-Zehnd interferometer, right? So you can just see that this is just some convoluted way of drawing a Mach-Zehnd interferometer. The only difference here that I want you to take away is that this Mach-Zehnd interferometer is physically standing up, so that gravity is pointed this way. And the atoms, because they carry mass, this can be used as a test bed for local variation of gravity, right? So in this kind of a situation, what this experiment arranges is that there are these two ports here. It's just a Mach-Zehnd interferometer for me, right? And one of them is a dark port, right? Which means I don't expect to see light in this, right? So let's go back to the comment that Rana made, right? All careful measurements that are made, preferably if they can be so arranged, are dark mode measurements, right? And so if gravity doesn't exist, that's all that's going to happen. But gravity does exist. And what that means is that these atoms are actually falling the entire time. They're not just doing this. They're not receiving a momentum kick and then passing, flying in a straight line. And instead, what they're doing is something that essentially looks like that, some poor cousin I'm drawing, right? And the difference between the areas of these two curves, basically, one of them being perfectly balanced, means that in this corresponding output, when you see light, it's actually an indication of the local gravity, right? And so that's something that you could take, and you could apply all this machinery to it. So you could decide to measure something. So a momentum mode, and then you can decide to measure some amount of atoms that you're receiving, and you could apply all of this machinery to it, right? So I wanted to discuss this more, but I'm grossly out of time, so I just stop. I just want to make 2-3 more comments for those of you, because all of us are physicists here. I think that these comments actually hopefully enrich your education, because this is one of the takeaway things that I want to say. Quantum metrology in general, basically, not only has received quite a lot of very interesting contributions from physics, where would it be without physics? But it also has given several things back. And one of the most interesting things that quantum information theory in general, but metrology has sharpened the tools that are then available for physics to use, is this notion of quantum fish information inside of quantum information per se. So I just want to make 3-4 comments and then I stop. So comment number 1, I leave this as homework to you. You can prove the following 2 comments. Statement number 1 is called the additivity of quantum fish information. Comment number 2 is convexity, which basically is the statement that the quantum fish information over an ensemble is always bounded, is convex. Right? So what are these two statements and why did I write them? So this simply is saying to you that if you're trying to determine you have two physical systems, two atoms, and the rate at which, or the curvature, the speed of the Hellinger distance or the Bures distance, the cousin of it, right? The variation of it, that's just the sum. Something's changing over here, something's changing over here. Just take them together, right? And the second is, it's a very classic information statement, right? And the second is basically it's saying you can't do better than pure states. So if you have a density matrix rho, so rho, if I write as sum over lambda I times lambda I, each of those is a pure state, right? And what it's saying is pure states have the best fission information. That's the reason why that statement is so important, because more often than not, if you don't know what to stick into the input port of an interferometer or the input port of a sensor, just stick pure states in there, because anything else will do worse. Right? It's a kind of grand statement you can make without ever knowing what the rest of this conversation is about, right? Okay, but I want to take this and run with it even further, or essentially just present to you some comments. The first comment that I want to make is this is by Lee and Luo, 2013, which is basically that if you have I'm writing it in some modern formula, but this is essentially the statement. So I've chosen as kind of an example the JZ, the collective JZ. What this means is it's sum over sigma Z I, right? So if you have individual Hamiltonians, right, and you have a density matrix, a bipartite density matrix, then basically, if this quantity is larger than n, basically like an n-partite density matrix, if this quantity is larger than n, then this is necessary and sufficient to prove that there is entanglement. It actually is a consequence of these two statements, right? Because the first statement here, essentially use the second statement first. First, break it into, so if rho, let's say, if I just do it for bipartite, so if I write F equals, let me consider a separable state, which is rho A tensor rho B. Let me just write this. Then basically when I apply, I get individual pieces, and the individual pieces cannot be larger than n, right? And so you can prove this by convexity. And so what this basically means is that what is this signaling at? What the signaling at is that if you take a many-body quantum system and you built a sensor out of it, you knew nothing about it, and you built a sensor out of it, and the sensor basically, the Fisher information that was produced, which means that you somehow judiciously, magically picked the right classical measurement, like unoptimized measurement. The Fisher information that you got was larger than n. You could stop right there and say that object has huge entanglement. It has, right? And in fact, Giza-Toth proved that there is genuine multipartite entanglement in this. So this is something that what it does is it takes your Fisher information knowledge and extends it into the theory of entanglement, which I think is interesting and perhaps worthwhile. So the very, very last thing I will say is that if you have basically, I want you to just consider this Hamiltonian for 1 second. Consider the Hamiltonian consider this Hamiltonian just for 1 second, right? If I draw a diagram to try and explain to you what the ground state of this object is, let me put H over here. H is some parameter. It's like a magnetic field, right? If I just put H over here, then and H equals 1, right? For H less than 1, let's say H is 0 just for a second, then this doesn't matter. And the ground state of this is the ground state of this Hamiltonian, right? And which you can convince yourself is like or all down states, right? On the other hand, if H is, let's say, 5,000 over here, right? What happens? This thing is the dominant object. And what's the ground state of it? It's some state that looks like that, right? Okay, just hang on to this idea for 1 second. And I just play a game with you for 2 minutes, and then we're out of here. So what I want to do is ask the question, what happens to the fidelity of this quantum state, of the ground state, psi ground of this model at a value of H, as opposed to psi ground at a value H plus DH? You can see the parameter estimation like setting that we're in, right? Something's varying a little, and now you're trying to calculate some distances, fidelities of two quantities, so on and so forth. This is easy to compute, and that's the reason why I'm asking. What is this? This is basically just, I take the up state and the sideways state, which is 0 plus 1 over square root 2, and I just take the modulus of it either to n or to 2n, depending on whether I define the fidelity with a square or not. I don't remember what I did last class, right? So this is basically if I have n particles. So this is the fidelity, which I'm realizing. So let me call it F with a bold. This is the fidelity F, right? Everyone in agreement? What is this number? Right? This is 1 over square root 2. Square is half to the power of n, which is 2 to the minus n. Agreed? So if I take the thermodynamic limit, what does the fidelity of neighboring states do? Right? And where? Neighboring states anywhere here and anywhere here. This is what I wanted to calculate. What happens is, let's calculate it over here. Over here, the ground state doesn't change, right? It's all downs, let's say all downs. I move a little, it's still all downs. So here the fidelity is all 1. Here at 5,000, it's all pointed sideways. I move a little, it's still all pointed sideways. So here the fidelity is all 1 again. What happens here? It drops down to 1 over 2 to the n, right? And what happens when n goes to infinity? 0. So the fidelity, if I overload this diagram, essentially does something like that, right? Now, I just want to write one formula and then we're done. What this means is that if I sit right here, if it's a magnetic field sensor sitting right here, a tiny variation in the magnetic field does something very crazy to my fidelity. You can capture this by calculating something called the fidelity susceptibility, which I just want to show you, is minus the log of the where h goes to h plus d epsilon. Again, this is a curvature-like object, right? And for this reason, I say to you that quantum phase transitions, which is what this physics is all about, right? The physics of the non-analytic behavior of certain properties of ground states of many-body Hamiltonians in the thermodynamic limit is also well studied with Fisher information, right? And in fact, there are entire reviews on this. Luigi Amico's the person that you should look for. Okay, so anyway, I had more things to say, but I stopped. I've already insisted on your patience quite a lot. So thank you very much. I'm still around tomorrow, so we can chat offline And thank you again to the organizers. This wonderful opportunity.
Thank you, Sai. Any questions?
I have one question. So, so you said that Fisher information can be a good measure of entanglement.
Yeah.
Does it differentiate between classical correlations and entanglement?
No. The statement is very specific. The statement, actually, this is a very good point. The statement is that if you have this kind of JZ-like Hamiltonians, right, sum over I sigma Zi, and if you see that your quantum system, your quantum state has a Fisher information larger than n, then this is signaling to you that there is entanglement in there. This is a very specific comment. How much entanglement, what variety of entanglement, which family of entanglement, no comments. Yeah, and so as in fact, as Carl said, like not all entanglement, GHG is the one that's actually really the useful, right? But the point here is basically that Fisher, I want us to think about Fisher, or I want to share how I think about Fisher. I think of Fisher in two separate ways, or I think of, in fact, quantum metrology in two separate ways, which is, what can I do for it and what can it do for me, right? And so what can I do for it is all of these formulas, to learn about quantum Fisher information, to share that with you, and also to kind of look at better sensors, design better sensors, so on and so forth. And what can it do for me is it can teach me a lot about entanglement theory, about quantum phase transitions, about condensed matter physics. It's all over the place. If you just open any modern condensed matter textbook, it's all over the place. And so I just wanted to end, in case this is something that some of you are interested in working on, novel condensed matter systems and quantum materials and so on and so forth, that this is a direction that is actually quite related. And so I just wanted to, now that we're here, just signal to it, nothing more than that. Yeah.
There's one more.
Excuse me.
So firstly, if we want to apply this for estimation, then this kind of picture, when you have a quite drastic phase transition at some tiny interval, so you need to know beforehand that the value at which this is happening and bring the system near to it.
Yes.
So then estimation, then
that's fine. It's still okay, no? If you know that you have an extremely quantum critical system around, let's say, I just pick a random number out of thin air, 1 Tesla, right? And if you have an extremely stable DC source, like static magnetic field of 1 Tesla, right, or 0.999 Tesla, and you just park it there, then it's actually quite sensitive to the difference, right? And in an amount that is exactly quantified by that, so that variation is quantified by that. And so in that sense, there is actually a whole literature. I, in fact, had references and more things to say, but I won't for now. I'll just share this with you in the notebook that I will provide. There is an entire field of essentially doing metrology with quantum critical systems. So here again, I just repeat the comment that Anil and I exchanged in his lecture. In quantum criticality, what is happening is there is something that is going off to infinity. Here, what is going off to infinity is the second derivative, right? So because that second derivative is going off to infinity, you have something going off to 0, the fidelity, but something else is going off to infinity. And so it's not the same, it's not the same variety of reducing, the variance of the unbiased estimator by basically designing your interferometer extremely carefully, so on and so forth. This is a completely different object. What this is you have some water that is just going to freeze. And now you use that residual heat that it needs to pick, freeze, so, release to become, right? Let's say the other way around, there is ice that is just about to melt. You use that residual heat that it needs to pick up, essentially as a very, very strong sensor for heat, right? What is it called? A bolometer, right? Yeah. So
yeah,
there's a Hindi joke somewhere in there, but go ahead.
One thing I missed, that you said this can be a witness of genuine n-partite entanglement?
A specific, very well-known result by Giza Toth. I can share this with you. Yeah.
Okay. Any other questions?
So sorry, I just want to clarify. It says that if Fisher is larger than n, then it means that there is genuine multipartiality.
No further questions or any other clarifications? I think we are hitting the limits.
Okay, we have already hit the limits.
Yes. So with that, we hand over another elephant. in the-
Thank you.